Okay, so sorry for some trouble initially. I don't know, something was happened with the browser. Anyway, so already we talked about some basics. I mean, some historical things and some motivational things about mathematics. And now you should know that there are four main branches of mathematics. One is number theory, which is very common. I think you might be knowing about it. Second one is algebra, okay, which is kind of you can think of uh, a similar flavor as the number theory, but in a different thing. Then there is another branch known as analysis, which is on the top of calculus, and the fourth branch is geometry. All other branches of mathematics are some combination of these branches, right? So these four pillars. So I think you need to know about basics as much as possible in these four pillars to really understand any ICT problem. Whether it is a signal system, communication, or it is a computer science. These four branches are very, very important. Okay. Now, calculus. So who invented calculus actually? Any idea? Huh?
It was in Kerala. You had given reading, but
Yeah. Okay. So I would say that Kerala, the first textbook was discovered. Obviously, it was there for long before that, and I think it is believed. And I think if you look at, there are a lot of mysterious things also. For example, uh, what is the largest man-made structure? How old it is? And where it is? All kind of things are there. Some people have found out it is 24,000 years. They have they find out something. All kind of controversies, debates, and so on and so forth. Right. And in South, there was, I don't know, people who are from Tamil Nadu, they might be knowing there is a land known as Kumari Vandaram. I don't know whether you know about it, right? It was ahead of Sri Lanka. So they say that before last ice age, it was all populated by humans and then it went into the sea. Anyway, so I was not there and I don't know. There are ways to find it out, but so it looks like, that most of these mathematical concepts, you can see that they are very, very sophisticated, right? And it is mathematics which you cannot change. Whether it is 25,000 years ago or 100,000 years ago, right? It will remain the same. It's a fact of the nature, right? So after the age of discovery, what Europeans call it, it appears that because the first textbook of mathematics, the calculus, appeared to be in this Kerala School of Mathematics and Astronomy. Yeah, okay. And it is believed that it is traveled to Europe via Middle East, because when I visited even Saudi Arabia, people call masale, spices, as Bharat. So that word is used there, it's very common. So basically, so all those old traditional, business was going on and so on and so forth. Anyway, so that is something interesting. So I'll show you after that what happened. So essentially, in terms of writing, Madhava proves the results about infinite sums, especially infinite series, which has sum pi by 4, right? These kind of things. That means there was idea of convergence already there, right? So this is something already known in India. So Madhava was born in 1350 and died in 1425. So a lot of mathematicians, especially in Ujjain also, in Gujarat, Ujjain, and other places, they used to see, basically in India, astronomy was very, very natural, right? They used to study a lot of things. They also used to make horoscopes and so on and so forth, right? To do all the calculations. And I think you can see that many interesting things are there, So Varamir, I don't know whether you heard about Varamir, so there is a book also you can read. So I think some of you can go to the library and read some of these books. Interesting books are there, okay? So that is something 600 years ago, right? And then this is the first textbook of calculus 1530. It has everything. I mean, I can post it. I have the PDF also if you want, but first I can share with you some of you. So it's the infinite series, expansion, power series, even Taylor series. So Taylor series, as it is after the name of Philip Taylor, right, from Europe. But all these things were already there in this book, which is 600 years old, right? So trigonometric series, test of convergence, value of pi up to 11 decimals, all fundamentals of calculus like differentiation, term by term integration, iterative methods for solutions of nonlinear equations, theory that the area under a curve is its integral, etc. Everything is given in this book. You can see yourself. Okay. So 600 years ago, right? But so after that, I think people believe that this book traveled to this masala route to Europe and so on and so forth, and people spend more time and develop it further and so on and so forth, right? So all kind of things are there, but these are the early evidence, but that there was a first textbook of calculus in India. This is the portion of this book, uh, in Malayalam, right? And I think after that, you can also read Principia Mathematica. It is available online, right? Okay, this book written by Newton. Okay, so this also talks about, actually, when you see, as you know, there is a debate who invented calculus, Newton or Leibniz, right? So there is a way of approaching the problem is different, slightly different actually, and then which one is more natural and so on. You can look at those things. So sorry, this was Leibniz, and then there was Isaac Newton. Yes, Principia Mathematica, right? So these two things are interesting. Now you can see that these are around 1686. Newton has written Principia Mathematica, okay, and a paper on calculus was written by Leibniz, right, in 1684. So almost 2 years difference with Newton, right? So that is interesting thing. So there is always a huge debate who invented calculus and so on. But as you know, it is well known already in India, but in a different form maybe. But ideas were there actually. So a more formal thing which I'm going to touch in this class is actually done by some other people, which I'm going to show you. And you will love it or you will hate it, but you cannot ignore it. Okay, you can love it or you hate it, right? So it is something. By the way, there is a nice documentary on birth of calculus. You can watch this YouTube link. Okay, so there is a timeline from 1600 to 1800. A lot of people worked. You see, after the paper by Leibniz and book by Newton, a lot of people started looking into these ideas, right? Even the Kepler was also there. I think who studied the motion, right, of the planets and so on in Europe. So many things happened after that. So Euler is one of them. Now I will show you a bunch of mathematicians who have done some contribution. So Euler from 1707 to 1783. I mean, a famous statement about him is, read Euler, he is master of us all. All the mathematicians used to refer. So he has done a lot of great discoveries actually. You can find many interesting things from Euler, and Jean Lee Albert. So I think you heard about his name, right? Somewhere. So as an exercise, I'm showing you the name of a mathematician. You can tell me what they have contributed in calculus, because you know calculus already, right? I'm probably going to give you a different flavor of calculus, but anyway. Lagrange has done a lot of work on even group theory and so on, right? But Laplace, a famous transformation after Laplace transformation you might have seen, right? Special kind of integration, which is really nice. Fourier. If you have not heard about Fourier, you have not done the engineering actually, right? So as I mentioned, basically there are functions which you can approximate with the combination of sine and cosine. This is the very basic discovery. While solving differential equations, actually Fourier encountered those things, right? And that gave us trigonometric series, what is known as Fourier series. Okay, the first one. And then after that, many such series were discovered. There is a nice book by Zygmunt, trigonometric series. if you are passionate about these series, you can look at this book, Zygmunt. I'll show you the name of that mathematician also. So basically, special kind of Fourier transform is used, for example, in your JPEG that you picture that you take from your mobile phone, right? All those JPG format uses uh, discrete cosine transform, right? I think a lot of applications are there. Poisson distribution is a very famous distribution, I think, if you know. Yeah, this is the guy actually, which probably you will either hate or love, because he actually fully rigorous epsilon delta definition of limit he gave. And we are only going to talk about these. So all those formulas for calculating limit, I don't know. And I think you also should not be knowing. You should know this rigorous approach of epsilon delta, which was done by this Bolzano, right? So a fully rigorous thing. And also he talked about intermediate value theorem. There is a famous theorem also, Bolzano-Weierstrass theorem on his name. Okay, so this I'm going. So I love this person actually. I think you will also love after some time. And Weierstrass is sort of my hero, because I'll show you a monster what he created. It's very beautiful monster. Beautiful things are useful actually. So I'll talk about this Weierstrass function actually. And he also talked about epsilon delta definition of limit. You know, Weierstrass theorem. There are many results from Weierstrass anyway, but I think I have mentioned some of them here. Cauchy, yeah. So this name you might have heard by now. The man who taught rigorous analysis to whole Europe. Around 800 papers, 5 textbooks. More concepts theorem have been named for Cauchy than any other mathematician. A lot of things. So his name is forever, right? These are two popular things. Post reanalyze, that book that he wrote. Okay. So Cauchy is a great mathematician anyway. You will see even in the complex many things contributed by him. Riemann. So again, I think some of you might have seen from the last lecture. There are 7 problems. One of them which can give you $1 million each, right? So one of them was Riemann hypothesis, that summation n is equal to 1 to infinity 1 over n is power z, where z is a complex number. If this function is zeta z, the zeros of this function lies on the line real part of z is equal to half. It's still unproven. If you can prove it, you can get $1 million. Forget about $1 million, you will be world famous immediately, right? So that is more prestige than money. And so those who are interested in Riemann zeta function, I mean, you can look at it. There is a book in the library, a small book, which talks about Riemann zeta function. And Riemann has done many great things anyway. So actually he said that the zeros of this function will lie on this line, and he has a beautiful relationship between the zeta z and the other, sort of function relationship. And the space is limited, so he's not able to write. Sometime he will write the proof or something, and he never wrote. And since then, it's a mystery. And people are trying to prove this Riemann hypothesis. In order to prove this, they have developed a lot of mathematics, beautiful mathematics, right, which is there. Paul Frederick Gauss, a famous book by him on number theory, which is available if you want to read it. It's the right, very good thing. And also he has done a lot of work in calculus also. Yeah, this guy has studied properties of real numbers, the real line. One very famous thing that he contributed is known as Dedekind cuts. So I think some of you can explore what are these Dedekind cuts on the real line, right? All these Dedekind cuts and etc. you can find in the book a course in pure mathematics by G.H. Hardy. That book has most of the stuff there, right? Hilbert. Now you see, as you know, you are studying BTech in ICT or whatever, it is because of this man. Because if he has never asked this question, that is there any mathematical procedure through which truth or falsity of any statement can be derived, and that resulted in Turing machine, the birth of computer science. So he asked those 23 questions in 1900 in International Congress of Mathematicians in Paris. And I think I respect him because there's so many great things he has done. And now there is a response from Hilbert, Hilbert responded upon hearing that one of his students had dropped out to study poetry. So his response, good, he did not have enough imagination to become a mathematician, right? So if somebody is studying poetry and all these things, they don't have that enough imagination, right? Dirichlet, there are many conditions you will see. He has also contributed a lot in different parts of calculus. Cantor, people who used to say that this guy is mad. So you see, if you are counting how many points are there on real line. How many points are there on real line? Real line, you know, right? How many points are there? Infinitely many. But if you take a interval, say closed interval 0, 1, how many points are there? Infinite. Which infinite is bigger? All kind of questions, So he answered many mysterious things. The first time he wrote that paper, it's a very famous paper. People said this guy is mad. I don't know what he's talking about. But later people realized that he was talking in the real sense. Okay. So some of you can probably, so for example, natural numbers, 1, 2, 3, 4, 5, they are also infinite, right? So the cardinality of natural numbers, people call it LF naught. Cardinality of real numbers, they call it C. Which one is bigger? Okay, C or LF naught? All kind of interesting questions are there. Anyway, so it's beautiful work. In fact, he has also, I'm going to talk about one of his beautiful idea, Cantor diagonalization process, which is very famous in computer science. And it is because of Cantor diagonalization process, we know there is a limit of a Turing machine. How much Turing machine can compute? Turing machine is your first computer, right? As I told you. Poincare was the last mathematician who knew all the mathematics up to his time. Okay. Even people said that people say that he has also discovered all the work that Einstein has done later on. Okay, but he never bothered to publish even. So that kind of people are there. So very great mathematician. Poincare has done a lot of work. Hardy. So Hardy you might be knowing because of Ramanujan, right? So he has said, I have never done anything useful. No discovery of mine has made or is likely to make directly or indirectly for good or ill. The least different to the world. But actually, most of his work is very useful. Okay. So as I mentioned, there is no difference between pure and applied mathematics. Whatever you can sell, that is applied mathematics. Whatever you cannot sell, that is pure mathematics. But whatever you cannot sell today, you can always sell it tomorrow. There is no difference between pure and applied, right? It's all mathematics, beautiful mathematics, right? Okay, so Whitaker Watson, they have written a nice book actually. He was advisor of G.H. Hardy. Watson, advisor of Whitaker actually. Forsyth has done a lot of work on differential equations and complex analysis. I don't have their pictures somehow, I don't know why. Hobson, there is a nice book, Theory of Functions of Real Variables. I think I mentioned in those lists. I mentioned a list, right? That he has done some nice work in that book. Zygmunt, I mentioned about the trigonometric series book written by Zygmunt, which is very important. If you want to work on the medical imaging area, like CT scan, MRI, this book is very useful by Zygmunt. Okay. Okay, so I think this is all historical perspective. Now, I will show you some broader applications. I cannot cover all of it. I have limitations. And we have to start the class also, right? We cannot keep on talking about history, but at least some nice applications. So what are the building blocks of infinitesimal calculus, right? By the way, yeah, so I think I told you about these statements, right? These are very important to keep in mind by great mathematician Richard W. Hamming. So essentially, limit, continuity, differentiability, integration. These are the four concepts. And we need to do all these four concepts through Bolzano's ideas of epsilon delta. So I think by the end of the course, you will remember what is epsilon delta. We are not going to do any calculation business. Integrate this, differentiate this, find this limit. No. If I say find this limit, I will say using epsilon delta. So that idea is very important, very beautiful idea actually. Okay. And I will, you will feel that actually, okay, that's something really very, very interesting. Now, there are unlimited applications, okay? Calculus is everywhere. I think some of you might have seen this book. It is in the library, right? How to see the math in our coffee, on the highway, and even in the night sky. Okay. The most effective number of hours of sleep and the fastest route to get to work. Determining which seat at the theater leads to the best viewing experience. All this can be handled by calculus. Okay. Some beautiful Sunday readings with a cup of tea you can enjoy. Even zombies and calculus. Calculus of happiness. Okay. All kind of things. So some of these books you can buy or you can maybe get in library and enjoy a cup of tea. What are the possibilities? Mathematics marries and finding somewhere to eat can be handled with calculus. Even the restaurant finding, right? Why you need math to dance? For dance, you require this. Maximizing profit. This is very common business application, right? You want to maximize the profit. Cooking a potato can be done with calculus. Okay. Love affairs can be described in terms of calculus. I will sometime tell you how to model this. Okay. Even marriage. This is a nice book by Hannah, Mathematics of Love. You can look at it. And this is the book, Mathematics of Marriage. You can even predict when there will be divorce using calculus. Right. So you can actually, start a company. Okay. In plain bolding, right? So there is a nice paper by one of my friend Anuj Mobai. So he was in US when they wrote this paper. So at the time of epidemic, how to board the plane so that the infection rate is minimum. Those can be determined by calculus, right? So it's a really beautiful thing. Some beautiful integral transforms, and each of them has wider applications. I don't have time to go for each of them, but as I mentioned, Fourier transform has plenty of applications. I will just talk about, I think wavelet, each of them has a lot of applications, right? So if you just look at these integral transforms, you'll find wider applications everywhere. But I can talk about Redon transformation. So what is Redon transformation? So Redon discovered in 1917. This is the paper you can read on your own. Okay, and it has applications CT scan. It is because of this CT scan technology was developed, and people who did that, they got Nobel Prize. Pre mathematics का यही नतीजा है, right? So somebody is developed and other people will use it. So if you use your own mathematics, then you can get benefit. Anyway, so that is something. Again, there is a nice book, How Calculus Reveals the Secret of the Universe, Infinite Powers. Okay. There is a website, calculus.org, which has a lot of resources on it, so you can just look at it. Symbolic computing tools will help you in visualizing. There are two popular tools. One is MATLAB. How many of you know about MATLAB? Okay, very good. So MATLAB was developed by Cleve Muller. So I have communicated with him a couple of times, but Cleve was teaching a course on numerical methods to his students, and one of the students said that why don't, since these things have so many applications and you have already written a program, we can make a company out of it. And then they found MATLAB. Now they are doing a lot of business. Okay, using mathematics, right? So you can see actually, and we have a campus-wide license, so you can actually use it nicely. Okay. Another one is Mathematica by Stephen Wolfram. Wolfram is another great mathematician. I think at the age of 19 or maybe 18, he did his PhD, and he started his company pretty soon because while he wanted to understand cellular automata, which is another beautiful thing, and there is a book written by him, It's kind of, I forget the title actually, by the way. It's like applications everywhere kind of thing, mathematics application everywhere kind of thing. It is something, a new kind of science. Yeah, the book title of the book is New Kind of Science, which talks about these cellular automata things can simulate anything basically. In fact, he observed that some of the cellular automata simulation can lead to non-linearity, chaos, and all other kind of complexity that you observe in the nature, right, while writing the programs. And that resulted that he formed the company Wolfram, and Wolfram is now a very good company. I mean, doing a lot of things, Mathematica. I think sometimes CD in your iPhone, if you use, it was using Wolfram at the back end, Wolfram engine. By the way, how many of you are able to compute sine of x cube? What was the answer? I will show you the answer, but how to arrive at it, let you discover yourself, right? As I mentioned, right, if I give you fish, you will never know how to catch the fish, right? So I will show you the answer anyway. Now, there are some intellectual challenges, and I love these challenges. You will encounter more and more such things in your course throughout 4 months. These are known as, and most of them I'll give you as a tea time problems, right? So, for example, if I ask you, can you give an example of a continuous function everywhere on the real line which has no differentiation anywhere? Continuous everywhere on the real line, but nowhere differentiable. Okay, this is just one example. And you see, so actually I'll just quote Henry Poincaré. Logic sometimes makes monsters. For half a century, we have seen a mass of bizarre functions which appear to be forced to resemble as little as possible honest functions which serve some purpose. More of continuity, okay? Less of continuity, more of differentiation, less of differentiation, and so forth, right? So actually, he is saying that in former times, when one invented a new function, it was for a practical purposes. Today, one invents them purposefully to show up defects in reasoning for our fathers, and one will deduce from them only that. So basically, uh, now people are introducing these functions for fun. But actually, there are, as I mentioned, whatever is discovered today can be sold tomorrow. Even the V-stars function is quite useful. I can show you. So what is the V-stars function? Here is the first example. You see, this is the function. F of x is equal to summation n is equal to 0 to infinity cos of 3 raised to power n x divided by 2 raised to power n. X is a real number. See the beautiful function. Now you see the interesting property. If you look at the function globally or look at it a small portion locally, it looks exactly the same. This function is continuous everywhere and nowhere differentiable. You cannot find a tangent. So T time problem, show that you cannot find a tangent on this. That will be beauty. See, you will learn entire calculus by doing these pathological examples. Rest thing is very trivial, right? Can you show that this function, you cannot find a tangent anywhere on the real line, right? It is not differentiable anywhere on the real line. This is first example. I love this because it has a lot of connection with computer science. Also, it has some connection with the stock market, by the way. So anyway. Now give an example of a real valued function which is discontinuous everywhere on the real line. Not continuous anywhere on the real line. You see, this is the example. Right? Is 1 if x is rational and 0 if x is sort of, it is telling wherever it is placing 1 whenever there is a rational number. Otherwise, it is 0 on the real line. Right? This is another example. Then, so basically, you need to prove all these facts, whatever I am telling you. This is an example of a real valued function which is continuous only at one point on the real line. And that is origin here. This is x if x is rational, 0 otherwise. This function is continuous only at origin, nowhere else. This I have not given you, but you need to find out. Give an example of a real valued function which is differentiable only at one point on the real line. Differentiable only at one point on the real line. Okay. And by the way, you must have heard about Maclaurin series, right? Maclaurin series, padha? Nahi? Yeah, so this function is differentiable infinitely many times, but no Maclaurin series exist. That's another beautiful thing. So these are some, I only gave you 5 pathological examples to give you the flavor of calculus that we are going to do. Rather than simple calculations, limit, substitution, this, that, right? Okay. So you will enjoy the beauty. These are all beautiful functions, right? So this actually, you will be reading over the next 2 weeks, these sections from Thomas' book. I am going to cover a few tests actually in terms of infinite series and so on, right? So I'll talk about it. And then thanks to my collaborators, agencies, my students. These are my current students who have done a lot of good work. These are my alumni from our lab, so who are at different places all over the globe. And I think you might have subscribed, right? So I think now I'll give you 1 minute. I think then we can start. Yes. Any question you have? Any question? You need to ask. I have given you already reading material also, right? So you need to ask and interact. You see, this is not a school where you need to spoon feed everything, right? No, you have to do the efforts, right? Because we need to train you so that you can swim alone rather than, dependent on someone all the time. Okay, so please ask questions, clear your doubts, right? I can show you that integration thing now, huh? Sine of x cube. By the way, Wolfram and we had a dinner at a long time ago, actually, I'm going to Wolfram Computational Intelligence Engine. Online integral calculator he has developed. So all your job is very easy, right? Just go here, delete this, and then go here. Right? This is the function which I gave. Now look at the answer and see if you can find the answer by on your own, right? See the beautiful answer? Right? I times x of square cube root of I times x cube gamma. What is this gamma? Gamma is the incomplete gamma function. Anyway, so I hope you will enjoy the path. I have shown you the goal, where to reach, right? Have you ever imagined this kind of solution? Now it's all for you to explore. Walk on the way, right? Discuss on the WhatsApp group, Man Ki Baat, right? And enjoy. Anyway, so you can find anything here. It's a very useful calculator developed by Wolfram. Now, now I'm going to start the actual things. Basically, first I need to understand the number system well, right? What is this number system? So can you tell me why we need natural numbers? Natural numbers, Huh? 1, 2, 3, 4. Why do we need them? Who invented them? Any idea? No idea. I mean, it is believed that in India it was invented and so on and so forth, right? It's given in Vedas. Because zero is given in Vedas, I think you might be knowing this, but so basically, when the society was developing, I'm just making a story. When the society was developing, probably people started doing business because mathematics is strongly related to business, right? And people started doing business, so they need to count. I have 10 cows. That guy has 20 goats, and so on, right? That counting developed. Okay, it is believed that counting developed, and then the business has. So basically, it resulted in what is known as natural numbers. Okay, so I will not be able to write anything. There is some problem here. Well, if we cannot write, then what to do? Anyway, anyway, so okay, let me speak. What else we can say? So there were natural numbers, capital N, we denoted by capital N is equal to 1, 2, 3, 4, 5, 6, and so on, right? Infinitely many. Right. So then there were equations that emerged such that x plus 2 is equal to 0. How will you solve over the natural numbers? You cannot solve. So it is the business which push the limit of mathematics. They say that, okay, we should define now negative numbers. And so that resulted in integers. Of course, 0 was discovered a bit late, but set of integers denoted by Z. Z is a word for Zerling. Zerling means integers in German, right? So Z stands for 0, plus minus 1, plus minus 2, plus minus 3, and so on. Right? Means if you draw the real line, middle there is a 0, then plus 1, plus 2, plus 3, so on one side, minus 1, minus 2, minus 3, minus 4, and so on another side. These are the integer values on the real line, right? I mean, you can imagine, right? I mean, there is no need to write, right? Imagination is the best thing. Now, business was going because now x plus 2 is equal to 0 can be solved, right? So s equal to minus 2 is there. Then there are what kind of problems, equations do you think will not be able to solve on integers? Yes. Yeah, 2x is equal to 1. 2x. What number I should multiply to 2 so that I can get 1? And that question was not able, we were not able to answer through integers, right? So we need to extend the domain. And we got into what is known as rational numbers, Q. Standard notation Q. Set of all rational numbers, right? So of the form P by Q, where P and Q are integers and Q is not equal to 0, right? Rational numbers. I asked you pi is rational or irrational? I gave you one T problem, right? So I think you must be remembering anyway. So now, again, business was going on. Then there were other kind of equations which we cannot solve on rationals. By the way, a very popular thing that people say, the root 2, square root of 2 is what? Irrational. That proof you might have done, right? Anyway, so there are equations like x square is equal to 2, which has no solution on the rationals. Or rationals, it is a solution. Is it square root of 2 is rational number or irrational number? How do you identify? Huh? Irrational number. Very good. So basically, how do you identify if a number is rational or irrational? You just write down the decimal expansion. This is a very natural definition, right? Write down the decimal expansion of the number. If the decimal expansion of the number terminates or appear periodically, then it is a rational number. For example, 1 by 3 is what? 0.33333, keep on going, right? That's a rational number, right? The square root of 2 is a irrational number because it does not repeat, right? Or not neither terminate. So there are examples of rational and irrational numbers. So that means we got real line. Real line consisting of rational and irrational numbers both. And believe me, real line is beautiful line. I can give a whole course on real line, such a beautiful thing, right? So many things are there. Okay. So, but we don't have that time, but so at least you can look at G.H. Hardy book, initial some chapters, or you can also look at this book by, these things are not given in those normal engineering books. They will not have this beautiful flavor. They only do calculations, okay? So if you look at the book by Goldberg, Methods of Real Analysis, initial few things, few pages you can capture. Or G.H. Hardy is enough, basically, okay? Which talks about this beautiful idea of real line. See, if you understand the real line really well, your foundations are strong. You can build anything on the top of it. Foundations in yoga, so what will you build, right? So by the way, are there equations for which we cannot solve on the real line? X square plus 1 is equal to 0 is the equation which we cannot, and I think I mentioned you that is a beautiful thing again discovered. X is equal to square root of minus 1 is not there anywhere on the real line. It's the imaginary number, right? And that discovered complex numbers. C is equal to A plus IB such that A and B belongs to real. And I is the root of the equation x square plus 1 is equal to 0, right? That's complex number. So are there any equations which we cannot solve on complex numbers? See, it's a mathematical curiosity all the time. Can we do further? Can we go further? So by the way, answer is there is no need. I mean, all equations over reals or complex, you will be able to find solution in complex. Essentially, it is said that complex numbers is nothing but a splitting field. What do you mean by splitting field? Any polynomial will split into factors over this field. Right? Now, how many number system, how many things I told you about? N, natural numbers, Z, integers, Q, rationals, reals, complex. 5 things. Out of these 5 items, where you can play and where you cannot play with everything. So for example, if you go to football field, you can play with football. If you go to cricket field, you can play with cricket. But if you go to number field, so what are the number fields where you can play with all the 4 operations: addition, subtraction, multiplication, division? What are the out of these 5 things which I told you, where I can play with all the 4 operations? Huh? Can I do it in n natural numbers? No, delete it. Next, can I do it on integers? No, delete it. Next, q, set of rational numbers. Can I do it there? We can do everything: addition, subtraction, multiplication, division with rationals. So rationals is first example of what is known as field. So field is a set where we can play with all 4 operations. It's a very simple definition, right? So Q is a field, R is a field, real numbers is a field, C is a field. So Q, R, C are three examples of infinite fields, where infinite fields mean infinite number of elements, and where we can do all the four operations: addition, subtraction, multiplication, and division, right? Something very easy, right? Whereas N and Z are not field. That's why we are going to study in this course calculus on real line and calculus on complex numbers, right? Complex numbers, that is very, very important. One last tea time problem, because you have to drink tea also today, today in the evening, right? So we know that on the real line, there are two infinities, minus infinity and plus infinity, right? How many infinities are there on the complex plane? Complex plane. Complex, we call it as a plane, right? How many infinities are there in complex plane? So it's a beautiful tea time problem. Enjoy, and we'll meet in the next class.